Yeah, Dusty sent me this cool article this morning. Yeah. I mean, these articles are popping up all over the place, which is just so exciting for me and anybody who's interested in planetary science. James Webb Space Telescope has discovered something on a nearby exoplanet that could reshape our understanding of planetary evolution. I like that they're using this evolution word now all of a sudden. I think this is a really good sign. It's just such an exciting time. The planet that they found was something that is Neptune-like. What was bizarre is that first of all, this Neptune's very close to its host star, so it's losing a great deal of its material very quickly, right? And we've talked about this paradigm in terms of shaping the way that Neptunes transition to something more like super-Earths or sub-Neptunes to super-Earths. Of course, the Earth is so tiny compared to a Neptune that we haven't detected many Earths per se, but by extension, by induction, you could imagine that there's probably an evolutionary step possible there as well. One thing that was kind of interesting about this, I think this is why it made the headline, it's actually published in Nature this month, which is, of course, like the preeminent scientific journal. Let's say has the highest impact of all scientific journals. So this is pretty important stuff. And I think the reason it made the Nature headlines is because they found that there's actually this sort of atomized layer, clouds of silicates, right? So sand, clouds of sand, let's say. And that's really fascinating too, because you got to think about, a big portion of course, our crust and our mantle is silicate as well, right? And so you might think about the early stages in the evolution of a planet and how it develops that core. And I think that these silicates seem to have been developed through different reactions with the radiation that it's receiving from the sun. I mean, of course, there is silicon already present in whatever its precursors were, but that it would react with the oxygen in such a way to form these sands, because sand is really just silicon and oxygen, right? So is glass, for that matter. They're just slightly different arrangements. And so you see this evidence of something that could potentially lead to a deposition of layers of rock that would form a kind of rocky core that might end up looking, eventually down the road something like this place or some of the other rocky planets in our solar system. So anyways, I just see these all as incremental steps towards a very different paradigm of planetary formation it's just happening under our feet right now, and it's really exciting. So, and of course, I'm considering how to make this class next year, as it moves into the GE capacity, how we can make it more about hypothesis generation, because it's a big step that people don't really get a chance to do in science classes. Science classes are often a list of facts. And so I really want to find a way for you guys to participate in coming up with your own models for how potentially different ways, not necessarily correct, but possible ways that the different planets could have formed other than the standard 1700s model that is persisting in our textbook. I think that'd be really fun. And important, because by the time that most people make it through the scientific pipeline, they get their PhDs, by the time they show up at grad school to do PhDs, they probably haven't done a lot of hypothesis generating, right? Probably just reciting a lot of things that people taught them. And that's really tragic, because sort of your success or failure as a scientist comes down to your imagination and whether you can think of new things to check out about the system you're studying. And most of them will be wrong, and that's fine. That's a huge, important part of it. So I'm not really concerned with whether we're right or wrong about these ideas. We can sort that out through different observational tests and so forth. But anyways, it's a cool moment, so I'm glad that you brought that to me. And if you guys find any cool headlines in the future, keep sending them along. I'm sort of aggregating these things and trying to keep tabs on it myself. Any questions about that? We'll recap all this. So Thursday, I don't know, maybe we won't, maybe Thursday will be kind of a shorter class, I don't know. But I basically want to recap the main points of this whole class, and in some sense we'll go through this evolutionary paradigm a little bit more. But yeah, it's a really cool moment. I'm really excited to be here and exploring it with you guys. All right, so in terms of what we did last week, I guess it was, yes, last week, talked about more moons. We talked about a lot of different moons, but the last class we talked about Saturn in particular for the most of the time. And the two moons that we really explored on Saturn that couldn't have been more different were Titan and Enceladus. And the rings, of course. Can anybody remind me some interesting, maybe differences or some differences between Titan and Enceladus, or something curious about the ring structure that we could just bounce off of? Because where we're going to go today is we have one last body of importance, which is Pluto, and then we're going to talk about asteroids and comets. So this is finishing up our planetary discussion, the last of the moons. What do you guys remember? What's some obvious differences between Titan and Enceladus? Yeah.
Titan is mostly nitrogen and close to our density, and Enceladus, the thing with it that struck me was the geysers spewing the liquid material from what appeared to be a subterranean ocean.
Yeah, so then that's the thing that we've seen over and over too, right? This subterranean ocean is really quite fascinating. In particular because, well, you can imagine that if this thing were in a warmer conditions, that maybe that would appear more as an atmosphere, a very water-rich atmosphere, maybe liquid water like on our planet, be very, very different. And these things are tiny too, so it's very unlikely we're going to see any of them with these James Webb's, with the level of technology we have in telescopes right now. We just can't see tiny things. So maybe there's a lot of these. Maybe there's free-floating ones around planets, we just can't see them. And then about Titan, what do you remember about Titan? You mentioned the nitrogen atmosphere. What else is interesting? It's huge, right?
Yellow.
In yellow, yeah. What do you remember seeing?
I feel like I'm recalling something about it having the densest or largest atmospheres.
Yeah, it's actually the only moon with a really thick atmosphere, which is interesting. The one thing I remember that's really bizarre is it has these methane lakes all over it, which is wholly unique. It's actually the only body in the solar system other than this place that has liquid stuff on the surface, right? Flowing liquids on the surface. That's completely unique. And of course, it's not water. It's very cold out there, but it is this methane stuff, so you can almost imagine it as like oil fields if you want. Pretty wild stuff. So those are two interesting places. And like you said, Enceladus has these geysers. That makes it, of course, a really hot spot for bio-hopeful people, right? People looking for origins of life or looking for life at other places in the solar system. Because, of course, those geysers have all of those nice features, salts, right? Warmth, potentially, water, obviously. And so I think we'll see more and more attention given to these moons that have, also you have a natural rip in the crust, right, that's gushing out liquids, so you can potentially go and taste that substance without actually having to dig down underneath kilometers of ice, which makes it pretty easy, relatively speaking, to examine it. Any more thoughts about Saturn, Titan? The Saturn rings are still a little bit of an open question too. I'm sorry we couldn't solve that issue for you. Maybe someone will propose something really cool next year if we open up these mysteries to people's imaginations. It seems like the most popular idea on and off is something like a destroyed moon, but we'll see how that holds up. Of course, another thing I didn't even mention, that Enceladus, of course, is generating its own ring in real time too, right? So there's the potential that they're kind of being constantly made by smaller bodies that maybe are no longer there, maybe bodies that appear that are grabbed up. A lot of Saturn's moons are rotating the wrong direction at weird angles, so there seems like there's some latecomers to the party. All right, any more thoughts? Yeah.
I have something in my notes about Saturn. I don't know if maybe it's just weird. Something about the atmosphere raining diamonds?
Yeah.
What was that?
Well, so carbon under extraordinary pressure, right, forms diamonds, and I think it has to do with the fact that the thing is enormous, and so there is some carbon signatures from Saturn, and the hypothesis is that due to the convection cycles, right, it's going to uplift some of this pressurized carbon, and you get this diamond rain, yeah, which, I mean, the pressures would be so painful that it'd be difficult to observe it anyways, and so you're not going to go there and get rich and collect it.
Theoretical.
Yeah, I think so, from what I can tell. I don't think it's wholly unique either. I think a lot of these exoplanets that people are seeing that have carbon signatures probably have a similar phenomenon going on.
Be more like snow than diamonds.
Yeah, probably. Way smaller, yeah. Way smaller, yeah. Yeah, snowflakes are pretty enormous, actually. You can see them with your eye. Yeah. I'm not sure what that lattice would look like. That's a really good question. I'll try to look into it more for next year, yeah. All right, let's kind of cruise through this because I want to have time to talk about, I want to finish up with comets. That's kind of the last thing we're talking about because comets, of course, are thought to, let's say, arise from the Oort cloud, which is an entirely hypothetical limit. It's like the shell on our solar system, which is basically a debris field. Maybe you can think of it as like a foam in between solar systems. So that's the absolute last thing that we can possibly talk about as we move outward. And so I want to get to those today. But let's check out Pluto really quickly because, well, if for no other reason than we've been to Pluto really recently and got some really incredible pictures of it. But Pluto does seem to fall into this same category of subsurface ocean moon looking thing, right? It's very, very similar. It turns out there's quite a few of these objects beyond Neptune that are free floating, let's say, orbiting the sun, but for whatever reason, they don't meet the mass threshold to be planets. And so when I was a kid, Pluto was a planet. They don't consider it a planet anymore. What do they call it? I think it's called a dwarf planet now. In other words, it's just not big enough. It's on the size scale of some of these moons. Let me see. I should have put this slide in earlier, but here, let's look at it in comparison to our own moon, right? It's basically on the same order of our own moon. It's very small, so it lost its privilege to be a planet. Okay. Its orbit's also a little bit wonky. It actually crosses the orbit of Neptune. So all of these bodies that are beyond Neptune and small and moon-like that don't orbit a planet, they're called trans-Neptune objects, or TNOs. There's quite a few of them, actually. And this one it just happens to be one that we're going to focus on. There's quite a few of these trans-Neptune objects. I think that's another reason why Pluto lost its privilege to be part of the planet party. It's actually, like I said, it crosses the orbit of Neptune, which is really interesting because ordinarily that would be a big problem, right? You could imagine that they would easily crash into one another and this would be a huge problem. But they're in this really stable resonance. They're in a 3-to-2 resonance, which, by the way, is a perfect fifth in music, which is quite interesting. And of course, our entire Western scale is built out of fifths. So it's a very, very fundamental resonance that occurs between the two. And the result of that is that it's essentially pulled out of the way every time that it's about to smash into Neptune. So that never, ever happens. So it's a very fortunate situation that it's found itself in. And that has to do, of course, with its distance in location. You know, it's stabilized at this particular location, and its mass with respect to Neptune and the sun. So it's again, there's so many of these things that seem like perfect coincidences. And of course, the reason, Newton and many of the very venerable early scientists were convinced that this was a sign that the universe was designed by somebody, right? Because everything was so perfect. Of course, Darwin came along and said, well, the reason things look so perfect is because everything that didn't look perfect got destroyed, right? And I think that's a very reasonable way of looking at it too. And I don't think that it removes the miraculousness of the situation we find ourselves in either, right? Because we are, sitting in this very, very ideal circumstance. Our solar system has been fine-tuned over billions and billions of years to remove everything that wasn't stable, right? And everything's been destroyed. And when we're going to talk about the asteroid belt in a minute here too, which certainly, there's again, it's a similar thing to the Saturn's ring. What's up with the asteroid belt? Is it the remnants of something that's been destroyed? Is it leftovers from something early on in the formation? Very hard to say, but you certainly have the sense that things in other solar systems, let's say circumstances that are not favorable to life or to even stable orbits, don't work out and they don't last for very long. So Pluto's there. It's in this strange. It has quite an inclination of its with respect to its orbital plane with respect to the ecliptic, which is quite interesting. I don't know that anybody knows what to make of these things. Perhaps that will stabilize over time. Perhaps it shifted relatively recently. I don't know. I don't know that anybody knows that. All right, what else can we say about Pluto? Oh, this is kind of interesting. Pluto, much like Uranus, is tilted on its side, right? So it's it has this 120-degree axial tilt, and the result of this, of course, is that, well, the result is that it's even during its day, one side is facing the sun, kind of at all times, right? It's South Pole, I guess you would say. Now, the question is, why did that happen, right? And it's interesting that the popular theory for why the thing's tilted on its side has to do with a concept called true polar wander, which is something that people tried on in the 50s to explain the ice ages here on Earth. So what's true polar wander? Well, true polar wander is kind of interesting. It's like the ice caps, the poles, are generally, let's say Pluto was at some point tilted properly, aligned with respect to most of the other planets. You know, it's aligned with the ecliptic, aligned with the sun, let's say. Well, over time, the ice kind of builds up in the cold regions at the poles, in particular at the North Pole. And let's say that it got a little top-heavy at some point. And as a result of that, you know, the thing is spinning, right? Most of these planets are spinning to varying degrees. Venus being a strange exception, very, very slow spin in the wrong direction. But the thing is spinning. And what happens is when you have a top-heavy top, right, it actually tends to fall over. And so the idea is that this happened to Pluto perhaps in the past. And so it sagged and fell on its side. Its actual spin axis shifted. The crust itself sort of drooped over. That's a really interesting idea, if for no other reason than people were really trying on this idea back in the 50s with respect to why we have these periodic glaciations on Earth, because we didn't always have them also, which is really strange. So I'm not sure the exact date that this all started, but some millions of years ago, not that many, some millions of years ago, we started to have regular 100,000 and then 40,000 year cycles of glaciers at the poles that crept down, covered the North America, and then receded. And we're in one of those recession periods right now where the Earth is quite warm. And presumably it will keep doing this. But we don't, you know, there's been struggle to understand why that's the case for a long time. And the prevailing theory is this Milankovitch cycles, which is really just the accumulation of all these different cosmic cycles. Everything from the precession of the way that the top of the Earth spin changes over thousands and thousands of years. There's been cosmic ray contributions as the Earth makes its way through different environments. The solar system makes its way through different environments. All sorts of explanations have been proposed. But there was an idea on the table originally that what happened was that the ice sheet would build up, it would get really heavy, and then the crust would slip and it would turn sideways and melt it. And then it would, you know, eventually reform, and the same thing would kind of repeat itself over and over again. And actually, the book that explores this is quite a really fascinating read, even just for entertainment purposes. It's called, it's escaping my mind. The author is Charles Hapgood. And I think it's called The Earth's Shifting Crust. And the foreword's written by Albert Einstein, which is really interesting. So Einstein tried to do a bunch of math to prove that this was possible, and he ultimately didn't succeed in doing that. So I think he walked back on his endorsement of this theory towards the end of his life. But it's still a really interesting, it's an interesting case of where people try on ideas that are kind of crazy, but don't, you know, necessarily move forward with them. So might not be the case with our crust, but it does seem to be possible in other situations. Of course, we know so little about Pluto, right? I think we've basically driven by it once with a really good camera, and so what can we say? We don't have the same level. And by the way, Einstein's eventual defeat of that theory came down to understanding the viscosity, so the slipperiness of the material underneath the crust. And he basically came down and eventually decided that it wasn't slippery enough. It was too sticky for that to happen. So we have no way of knowing those kinds of things about Pluto. It's just too early in our investigation. Cool stuff, though, nonetheless. Pluto was also one of those planets that was discovered kind of through math, right, as opposed to being actually outright seen. So people predicted that it should be there. Back in the 1840s, the first time this happened, of course, was with discovering Neptune by looking at these perturbations in Uranus. And the same thing was applied later on to find this planet X, they called it, back in the 1890s. And then it was eventually discovered. Somebody went looking for it at the proper place, and they found it. Actually, a 23-year-old dude named Clyde Tombaugh, which is pretty incredible. People really were in a hurry to get things done back then because they didn't make it that far, usually. 23, yeah. I mean, of course, there was just so much less, right? There was a lot more low-hanging fruit, I feel like, too. You know, when you know, the more you know about the universe, the more difficult it is to make advances. And you're also fighting against the full weight of people's belief in their complete understanding of situations when in all likelihood, they probably don't understand things. It's very difficult to fight against that, which is just a fascinating topic that I am always interested in exploring. Yeah.
If Pluto did shift like that, though, and fall, if it worked like a top, wouldn't that explain the orbit kind of shifted this way as well? Kind of.
Yeah, they should be related. I would agree. I mean, the one thing that people don't seem to understand very well, probably since we've never observed this happening, right? Most of these events we're just trying to reconstruct from the past. It's like trying to put together a murder from looking at the murder scene, right? Like looking at blood splatter and trying to make up a story, which, by the way, is notoriously wrong. Yeah, right? Like these things used to be considered forensic evidence, and now people are walking back on it. So it's really hard to reconstruct the past based on just walking into a room and just seeing what's there. And so the biggest problem that I can see is that people seem to think that these really stable patterns, these orbital resonances that I keep talking about, that, you know, every time somebody gets a tug at the exact right moment to keep that orbit perfectly balanced, right? They seem to think that these resonances require a really long time to develop. And so, you know, like I said, Pluto has a resonance with Neptune despite the fact that its axial tilt is wonky, its orbital plane is inclined in a strange way. And so my sense is that we don't understand the dynamics of how these orbital resonances go down exactly and how fast they might be able to be achieved. Or, you know, and the other aspect that we never ever talk about in these models is how often it doesn't work out, right? So how many other planets were like this and just got destroyed or got flung out of the solar system? They're just dancing around out in the Oort cloud somewhere, or they joined somebody else's solar system, or they were vaporized in interstellar space. There's no way to account for all of the things that we can't see. And so I think those are probably huge contributions. I think, you know, with respect to Darwin's biological theory of evolution, I think 99.9% of all the species that have ever existed are extinct, right? So we're only looking at the absolute cream of the crop that's around today. So you can't know what you can't see. And traditionally, especially in astrophysics and planetary science, we're trying to tell stories about what we can see. And this has led to these very uniformitary and very, you know, hyper-stabilized conservative models of how things formed. Well, they formed right there because it's unimaginable that they would have changed and then stabilized, right? So, yeah.
First ring don't make the noise, but if you keep doing it, the same pattern puts off that nice little hum.
Yeah, and how do you set it up, right? Maybe there's a lot of tries that are the wrong pattern, right? And those, we just can't see the remnants of those. So, very interesting. Now, Pluto has, it kind of has this brownish color, which is kind of interesting. Kind of similar to Mars, a little bit less red, more orangey. And this is thought to be due to the presence of those organic compounds, potentially these tholins, right, which people think may have abiotic origins, but they're also a sign of life here on our own planet, which is really interesting. It's kind of like this desert varnish stuff you see on these rocks. It's very much open for debate as to where that stuff comes from. So, I don't want to spend too much time on this. As you can see, just from its profile, the best theoretical reconstructions have the thing looking very much like some of these other moons that we've talked about, right? We've got this water ice crust, liquid water ocean, silicate core, No appreciable magnetic field, so probably nothing molten or doing any of those nice convection tricks that we've talked about over and over again. But honestly, the thing looks a great deal like many of the other moons we've looked at. It doesn't have active geysers, so again, probably nothing warming it from the interior. Let's see, very, very thin nitrogen, methane, carbon monoxide atmosphere. Surface pressure is 1 Pascal, so that's about 100,000 times less than our own surface pressure. By the way, we're all under extraordinary pressure from the atmosphere right now, which is quite easy to forget because, of course, the pressure on the inside of our bodies is the same as on the outside, so we don't feel it. It's equalized. But very, very low pressure, almost nothing there. This is kind of interesting. So in 2019, they checked out they were looking at the atmospheric pressure, and they found that it actually had lessened by 20% since 2016, which is incredible. So maybe it's just an exponential decay where if you lose a bunch of your atmosphere, the last few bits are just quite easy to lose. I don't know, but it seems to be depreciating rapidly. All right. People don't really understand the origins of Pluto. Early hypotheses concerned that it was an escaped moon of Neptune, but they weren't able to really make this happen in their models for whatever reason. All right, let's keep moving. Pluto's got some moons, by the way. Actually, one of the moons, Charon, is essentially not that much smaller than Pluto itself, which is, again, probably part of the reason we've deplanetized this thing. You can see that they actually orbit a common barycenter. It's not so much that Charon orbits Pluto so much as they orbit a center point, which you might be able to see here, that Pluto's wandering a bit. You might even consider them a double dwarf planet system, something like that. I'm going to skip through Charon because I want to make sure we have time for comets. So let's change gears here. This is probably something that will serve you well in the future because people are always mixing up these different things, and so let's make sure we set them straight. Try to remember one thing today. If you remember anything, let's try to make sense of the difference between asteroids, meteoroids, meteorites, and comets. At least let's get the difference between asteroids and comets if we get nothing else done. But let's try to make sense of meteorites and meteoroids. So, okay. An asteroid is actually just a tiny planet, okay? It orbits the sun primarily. And its orbit might be, like I said, a little wonky, and it might crash into other planets sometimes. This is a real danger with these tiny little planets. And so asteroids pose a serious threat to us here on Earth periodically. It seems like something like every 60 million years or so we get smacked with a pretty nasty one, which happened, from what we can tell, about 60 million years ago. And so that's why there's, of course, so much attention on tracking these things at this point. And to the extent that we have some time, we reviewed a little bit of the approaches at the beginning of this course about how we're trying to avoid these things and track them. And I'm going to highlight a couple more of those methods that are being entertained today if we have time. Okay, so those are asteroids. Now, meteoroids are much, much smaller, okay? So these things can range in size from a few grains of sand size things to stuff up to like a meter wide, okay? So that's the only difference between a meteoroid and an asteroid. Now, a meteorite is something that's actually cut through our atmosphere and landed on the ground, okay? So ite means it's here already, right? And oid means it's out there still. And then comets are in a wholly different class, right? These comets are actually kind of these ice ball things, right? They're originally called dirty snowballs, but they can vary and they can be more like snowy dirt balls also, right? So anything on that range, but they have a great deal of volatilizable elements, so waters and things like that can turn into gas. And so they have these wonderful plumes that we see when they come near the sun as it cooks them off. And comets tend to be, we'll deal with comets at the very end, but they tend to fall into two bins. One is comets that come by very regularly, so they're almost like planets in that they orbit the sun with some regular periodicity that's on a short scale. And then there's these really long period comets that can come by maybe only every few million years sometimes. And often comets get gobbled up by giant planets like Jupiter or the sun. And so part of the reason we even think there's an Oort cloud is because these comets keep coming despite them getting eaten very often by the larger bodies in the interior. So where do they come from? And the thought is, well, there must be some reservoir at the exterior of our solar system that's subject to getting kicks from other solar systems, which can dislodge these chunks of ice and rock and make their way into the interior, and we see them as comets. So those are our three broad classes: meteoroids, asteroids, and comets. But honestly, meteoroids and asteroids may as well be the same sort of thing. They're just on different size scales. Questions about that? All right. Now, most of the asteroids in our solar system are found in this region between Mars and Jupiter. We call it the asteroid belt. And we have tracked something like 1 million of these things, which are found in that gap. But they're not that much material altogether. If you added them all together, you'd only find something on the order of 3% of the mass of our own moon. Right? So it's a really tiny amount of stuff. And I think this is why people struggle with trying to these stories that talk about it, these hypotheses that maybe it's a destroyed planet or something. Well, it would be a really, really tiny planet were that the case. And it may be so. The other primary argument against that is that the asteroids are very different from one another. And so you see asteroids that are carbonaceous, you see ones that are very metallic, you see ones that are very silicate-rich, and so people think, well, these have to have different origins. And I'm not so sure I'm completely swayed by that argument because, of course, if you look at the Earth or something, it's got a lot of different layers, right? And so, if I was to take a hammer to the Earth, a very big hammer, I would end up with probably a lot of different pieces that didn't, bear much resemblance. I would have iron chunks, I would have silicate chunks, and so forth. So I don't know. The windows, the theoretical window is still open for me. There's also a couple of these asteroids, by the way, that really start to resemble planets themselves. This one in particular, Ceres over here, is very planetoid looking. It's actually a very difficult planet to explain because, I guess it's a mini planet. It's very difficult because it has this wonderfully rounded surface, but it's not big enough to have developed that rounded surface from the typical processes we think of as rounding out planets, right? So generally, we talked about this way at the beginning, and we'll do more of it next semester when we talk about stars, but why are these things spherical, right? Why is a planet spherical? And it turns out that it's this really nice balance between outward pressure and gravitational pressure that's just kind of push and pull at all sides. There's a tug of war at all surfaces, and it's perfectly balanced, right? And so the easiest way to minimize those tensions is to have a spherical surface. This is more or less the same idea with all spheres that you find in nature, with the exception of bubbles, which are kind of a surface tension modulation. But it's still a balance of tension in that case. Well, Ceres is only about 600 miles across. It's very, very tiny. It doesn't have enough gravity to uphold itself into a sphere like this, which is very, very strange. So nobody is entirely sure how this happens. But it seems to me like one of the biggest possibilities is that the thing used to be a lot bigger at some point in time, and its surface has eroded slowly over time. In that case, it would have the potential. So I don't know, maybe these things are extraordinarily old. We don't really know, except, our models are constrained by the age of our solar system, which is constrained by the radioactive dating, which is constrained by the fact that radioactive dating tells us the last time something was melted. So, and then it's ultimately constrained by the age of the universe, which is on the move again right now. So we don't know how old these things are. These are some of the most puzzled over bodies in the solar system, outside of the ones that are really, really far away. Yeah. Yep. Do you guys, anybody watch The Expanse? No? It's a good show. A little bit. Yeah, you should. First few seasons are really good. It's about asteroid mining, which we're going to talk about today quite a bit. Yeah, it's a very good show, yeah. It gets into kind of like weird, extraterrestrial weird stuff at the end, but the first few seasons are interesting. Yeah, exactly. So here's another interesting misconception. So you probably have seen like Star Wars or something where people are like, where these spaceships are like dodging all these asteroids and stuff. There's something like 100,000 kilometers between each one of these asteroids. So we've sent spacecraft out to Jupiter, right? And it's not like they were having to dodge asteroids on getting out there. So there's very, very few of these things, despite how it looks. I mean, it looks like it's totally clogged, but you got to think these things are tiny for the most part. We just looked at two of the biggest ones, and they were a few hundred miles across. Most of these things are very, very small, boulder size, tiny little things, right? So, and they're spaced out really, really far. It's hard to grip exactly how much distance there is. I mean, it takes years traveling at appreciable fractions of the speed of light just to reach out to some of these planets, right? We're going like thousands and thousands of kilometers an hour with these spacecraft, and it takes us years to get out to Jupiter. So the spacing is just hard to wrap your head around. So anyways, yeah, those spacecraft that have been out there, like Galileo, Cassini, Rosetta, New Horizons, they weren't dodging asteroids, okay? So it's not as dense as it looks like on this map. Let's talk about the different types of asteroids. It's kind of interesting. Like I said, this is one of the reasons that people argue that it's not a busted up moon or something. But I don't totally I don't grasp that argument very well. Maybe there's something I'm missing. But anyways, we see these three types for the most part. These carbonaceous types, which are kind of dark, the rocky silicate types, and then these metallic types. And these are, of course, very interesting to people because, well, they offer different ingredients for the things that people would like to do in space. And we're going to talk about the industrial applications of those in just a second. Skip this. Because the focus now in all reality has turned towards asteroid mining. And there's some interesting projects actually on the docket right now being proposed. Investors are actually putting together money for some of these missions as we speak, and there's been some interesting legislation proposed in the recent years that I want to highlight for you guys. I mean, these projects are thought to be like the amount of money it would cost to get to one of these asteroids and grab stuff and bring it home is going to cost a lot. It's going to cost hundreds of millions of dollars, maybe into the billion-dollar range, but what you're going to find here, and I'll go over some of the specifics with you, is that a single one of these asteroids, especially some of these asteroids that are rich in metals, especially the rare earths that we're right now sort of digging up from the Congo with child slaves, the abundance of wealth on a single one of these asteroids rivals the entire economy of the Earth in a year, right? So if you can pull it off and get some of this stuff back to Earth, it's actually hard to imagine how the material benefit that would provide to our planet. And I think in a good way, in particular, because if you think about our whole economy is actually, California has a program to move away from combustion engines, which is, sounds great they're supposed to do that by 2030, I think. They're not even going to sell combustion engines, which is a cool idea on its face, but it's like this battery technology is gnarly. Like it depends on really, really inhumane conditions for the mining of these rare earths. And so asteroids pose a potential alternative source in abundance of those. And so that's why people are turning their noses to these things. Yeah, go ahead.
The asteroids, they couldn't bring them back to the Earth.
Well, that's the thought. Yeah.
Destroying us.
Well, some people want to bring them back, yeah. And so there's a big argument about that, exactly. And I'll have more to say on that in a second. No, it's good. It's a good point. Yeah, so let's say half of the space people are worried about how to destroy asteroids when they get too close, and half of the people are worried about how to get them closer. So it's a very interesting tension. What's up? Yeah.
So when mining these asteroids, is equivalent to the entire global economy?
It's about, I'll go over one in particular. I think it's on the order of $20 trillion, so that's about a quarter of the global economy. Yeah.
Like how big of an asteroid is that comparatively? Is it one of the
They're all pretty small, yeah. The question is, the thing is that it just appears to have concentrated rare metals in a way that we don't have access to on Earth. So what you have to do if you want to get these rare metals, by the way, these rare metals are like absolutely integral to all of this stuff, right? The cell phones that everybody's using, all of our laptops, our computers, like this is the future of the world, right? People are not going to stop using computers anytime soon. In fact, they're going to use more and more and more of them, and we need these things. So not only is it an enormous piece of the global economy, it seems like it's an increasing share of the global economy, right? They're going to be increasingly important in the future of how people do their work, right? I mean, the idea that, I personally do almost all of my work from home, right? That's crazy from when I was a kid. Nobody would have even thought that was even sort of possible, but I don't think it's going away. I think that people's reliance on these technologies to participate in the economy of ideas and product development and everything else is only going to increase and increase and increase. So anyways, this is coming. This asteroid mining stuff is not the stuff of sci-fi, and that's part of the reason I recommended The Expanse to you guys, because with asteroid mining comes a whole sea of political considerations, right? And not just like partisan politics, but who are the people that are going to go do this, right? Traditionally, if you think about the people that mined stuff for us, right? It's been at the heart of a very abused population. There's another great book. It's called People's History of America, I believe. This is by Howard Zinn. That's probably not the right title. Anyways, if you look at the history of America, all of the basic civil rights ideas, all of the basic unionizing ideas, they all came from mining, right? These miners are just doing really dangerous, gnarly work, and oftentimes in the 1800s, when mining was really taking off, they were essentially the companies that owned the mines would set up as towns. They would force the workers to live in those towns. They would be relegated to buying products from the company's store. They would live in company housing. Basically, all their money would go back into the company. I mean, it was not appreciably different from old world slavery, let's say, considering something like the way that the pyramids were built in Egypt by most popular accounts. It was very similar circumstances. And there was a lot of violent clashes between the miners that eventually ended up setting up the basic union structure that's very prevalent in many factory and blue-collar industrial settings today. And so, again, who's going to be doing this really dangerous work, going out to these asteroids, setting up shop, living on bases on Ceres and so forth? And The Expanse does a really good job of exploring this because, well, of course, it's not the rich people that are going to be out there sticking their hands in the mud, right? And so there ends up being a lot of tension between these groups and so forth. And so those things have to be ironed out, of course, because it's going to make for a lot of conflict and violence otherwise, especially when there's such an enormous bread ticket on these asteroids. They're so very, very valuable. I can't. It's going to be interesting seeing how they negotiate this. What's that?
Beyond the gold rush. If we've ever
Yeah, hard to imagine. I mean, so there's a couple of things too. So the heavy metal ones are really, really interesting. They're also the most rare ones. So those are the M-type asteroids. The S-type asteroids are more common, but they have like 10 times less the rare metals. But they do have like nickel, cobalt, gold, platinum, rhodium, stuff like that. I mean, this is kind of crazy. So a small 10-meter asteroid contains about 650,000 kilograms of metal, and like something like 50 kilograms of the super rare metals like platinum and gold. So 10 meters, right? It's a lot and it's little, right? It's not an extraordinarily dangerous asteroid to us, especially as we'll look at here. Yeah, we'll have time. So we'll look at different asteroid avoidance methods, right? There's a lot of those under construction. It seems like there's many, many, many ways to actually control an asteroid's path. So I think that, there will probably be all sorts of safety protocols, but I think they will end up dragging these things back towards Earth and setting them in orbit, maybe around the moon, maybe around the Earth itself, and they'll mine them locally, I'd imagine. But we'll see. There's a class of these. So one of the first steps, of course, is trying to pick out the ones that are easily retrievable. And there's been some think tanks working on that for the past decade. Let's see. They searched through 9,000 of these. And these are ones that they could potentially mine and drag around with existing rocket technology. They found that 12 of them could be brought into an Earth-accessible orbit by changing their velocity by less than 500 meters per second. So they basically just kind of give them a little nudge and they can get them back to Earth, essentially, right? Using existing rocket, so using cheap rocket technology that we already have available. Now, some of those other asteroids could be used to mine more fuel out there, so you could set up different propulsion systems as well. I didn't mention the carboniferous types. They have organic compounds, carbon, phosphorus, things that we might expect to make other chemicals out of that we could use in our fuels. So perhaps there will be new stations set up to build better propulsion systems and more of these asteroids can be brought nearby. But yeah, ultimately it's going to be a real balance between, we want to take care of the planet, we want to take care of the people on the planet, and particularly the people that are responsible for giving us the raw materials for these products. And we haven't really figured out how to do that on Earth. Part of the reason is because they're mined from some place very far away. Of course, if we were mining all of these heavy metals from West Virginia, well, it would be a lot easier to regulate the work that goes on there. But if you're doing trade with a sort of sketchy government in the Congo, it's very difficult to oversee that regulation. That's one way to look at it. But if you're setting up shop in outer space and you're not even really part of a country at that point, who's going to oversee that? Who's going to regulate it? And that's a huge problem. So I want to zip forward a little bit here. So back in 1967, there was the first Outer Space Treaty, which I think I talked about when we were talking about the moon to some extent. And it was received by a bunch of different nations, but all of the nations that really mattered didn't sign this treaty. Which is funny because the Outer Space Treaty originally, this is only back in almost the 70s, explicitly and inherently prohibits the acquisition of territorial property rights. And so it allows people to extract resources, but it says you can't make a claim on them, right? So how's that going to play out, right? If if 10 different countries or companies show up to one of these rocks and they're each trying to drag it back and make use of it, that just seems like an absolute conflagration waiting to happen. Back in 2015, there was the U.S. Congress, House of Representatives, passed the Space Act, which is kind of interesting. So the law recognizes the right of U.S. citizens to own space resources they obtain and encourages the commercial exploration and utilization of these resources from asteroids. So I'm going to read you section 51.303 of that law, which says, a U.S. citizen engaged in commercial recovery of an asteroid resource or space resource under this chapter shall be entitled to any asteroid resource or space resource obtained, including to possess, own, transport, use, and sell the asteroid resource or space resource obtained in accordance with applicable law, including the international obligations of the United States, which are basically nothing. So you can go get an asteroid. If you can recruit people to help you get there and drag it back here and mine it, it's yours, basically, at least according to the US. But nobody else agrees with the US. So what's going to happen? Well, what if China wants that asteroid, right? So these things they've got to be sorted out. But of course, the impetus is coming from the private sector. They're more concerned with how are we going to do it, less than how's it going to work out once we do it. So these are huge challenges. They're challenges we haven't faced in modern history. I guess the United States is a really interesting case because we showed up here and there was an indigenous population, but there wasn't an advanced civilization that was also pushing back for resources. And so the various colonies colonial empires fought against each other, but there wasn't that big of a struggle, right? Ultimately, I think we bought like half of the United States from France for like pennies, right? For nothing. And so basically that, and the British weren't that big of a threat. The colonists pushed them out pretty easily a couple of times, because it's just very difficult for these superpowers to manage something that was so far away. The ocean was essentially the outer space for these people. And so it was very difficult to manage those kind of resistance movements. Now, if everybody is vying for the same product, how's that going to go down? How's it going to be regulated? I don't know. It really opens the doors to some interesting, some terrifying Star Wars opportunities in the future. But again, that's the thing. People have historically fought over resources. It's like, what does everybody want? They want claims on resources, right? And I don't think it's so much power. It's just this idea of securing the future for their population. They want access to the resources. They want to know that they can persist into the future. So I don't know. And I mean, it might be a case where there's enough of these things that every country and at least initially, that each group can grab one and work on it by themselves. I mean, I don't understand necessarily how that's going to play out. I don't think that anybody does. So,
You'd think it'd be dangerous to be the one to actually figure out how to bring it back, because you can spend all the money you want on that. There's going to be people spending just as much money on taking it.
Yeah, once you get there, right? And so the kind of scary part about that too is if you read in between the lines of that legislation that was passed in 2015, by the Trump administration, the subtone is that the U.S. will support you, right? So that means if somebody comes, look, if somebody attacks a U.S. vessel crossing an ocean, like say the Lusitania or something back in the start of World War I, that's essentially tantamount to declaring war on the United States. So if somebody's out there from the United States, an independent enterprising venture, and they set up shop on one of these asteroids and somebody comes and tries to take it from them, well, now all of a sudden the U.S. is involved in essentially a war with that country. That's what I'm reading between the lines of that. So it's a tricky situation. I mean,
you'd have to figure it would be that much of a power play to get it, especially the early ones, because you could have a lot of determination that it would be worth a lot of our countries
to protect it, yeah.
go after it.
Yeah.
If it was, we'd have to land it in the ocean. We're not going to land it.
Well, I think they're going to just orbit it.
Oh, okay.
Yeah.
Oh, and then
Yeah.
it'd be a lot easier.
Because things burn up and break up in the atmosphere. You can't get them back down here.
That's
Yeah.
what I did.
So it would be a slow trickle. And honestly, I think that by the time this happens, it will accompany industrial manufacturing operations set up in orbit. So it's not going to be like people are basically going to be building, I don't know how to break this to everybody, but space is definitely the new frontier, just like the United States, just like America was at some point in time. People are going to be developing actual industries in space. It's not like they're going to be making all of these heavy metals and bringing them back to Earth necessarily. They're going to be using a lot of those to do more space exploration, more development of space projects, the moon, eventually Mars. But there's going to be cruise ships in space, right? There's going to be a whole world out there, and it's going to be built by resources for lack of a better word, from space, as opposed to digging up stuff on Earth and trying to bring it up there, which is extraordinary. The most expensive part about space work right now is getting out of our atmosphere. It's a really thick atmosphere, relatively speaking, and so gravity is not that big of a deal, but getting through that atmosphere is really, really hard, and that's a good thing because it means it's really hard to get down to us too. So most of the meteors and asteroids, the little ones anyways, they burn up in the atmosphere, right? And so that's a good thing, but it makes it very difficult for us to do work in space and to assemble things. So I think a lot of the industry will stay in space. Maybe some basic resources will be returned. I could imagine, 50 kilograms of rare metals would go a long way on Earth, and so maybe something on that order could be returned through some craft. But in general, a lot of these resources will be left there and be used for those projects out there. I wanted to touch really briefly on some interstellar asteroids too. This is a new concept that's popped up in the news recently. And did anybody see this stuff about Oumuamua by any chance? Okay, so it used to be, at least when I would have been taking this class in college, that we pretty much thought that the solar system was completely self-contained. Nothing ever came from outside of the solar system. That turned out to be completely untenable in the last decade because, well, for one, we've tracked a number of objects that came on these very hyperbolic trajectories, so open ellipses, right, beyond the scale of our solar system. And we saw one in particular that was very, very strange, and they named it after, I believe this is like a Hawaiian deity, Oumuamua. And this thing came in, it's very strange. It comes into the sun and takes basically a right turn at the sun and then leaves. And you know, this was really, really strange, and people tried to give it all sorts of natural explanations. It's also a very strange shaped asteroid. It was shaped kind of like a cigar. I think I'll show you a picture of it here in a minute. But one particular gentleman was by the way, this is what I mean by these different ellipses. So obviously, if you have a circle and you keep making it more elliptical and more elliptical, at some point it basically turns into a parabola. And that's what we saw with the Oumuamua. So this was back in 2018, by the way, when this thing made its pass by. What's really interesting is that in order to take this right turn, the main explanation that's used is that, well, it had some volatile compounds inside that became gas when it got near the sun, and it's basically like a comet. It ejected some material out of it, pushed it away from the sun. But they never actually observed any sorts of tails of gases or anything like that. And so there's also no evidence that its spin changed as you would expect. It's basically a tube, so if one part of it starts shooting out gas from it, it's going to start tumbling in an interesting way, and it didn't seem to do that. So people, to this day, remain very, very puzzled about what this thing is. And there's this one particular astronomer, this guy who's really interesting. I've had him on our podcast a couple of times now. Not a crazy dude, but he's completely convinced that these things are essentially the product of some extraterrestrial civilization. Now, what I mean by he's not a crazy dude is that he was the longest standing chair of the Harvard Astrophysics Department. So he's a legit scientist, and he's absolutely thoroughly convinced that this thing is basically either a piece of junk or something like a drone from some extra solar system civilization, which is really wild. So if you're into that stuff, you should check out Avi Loeb. He's a really interesting guy. He's got lots and lots to say about this. He's actually he's found he's found 3 objects now too, which appear to have crashed into the Earth from outside of our solar system, which was before Avi's work was essentially considered, well, Avi aggregated it, let's say, but essentially the people who discovered this tracked down the US Defense Department's satellite data and found basically some objects that weren't known about before. And they appear to be on these trajectories that come from outside of our solar system. So it seems like things do crash into our planet periodically from outside, from other solar systems. And Avi actually just went on a mission out. They took a boat out to, I think, Papua New Guinea, on the other side of the world. And they trawled the bottom of the ocean and tried to find this meteor. And they were going to examine it. Now, a lot of the astrophysics community is really upset with Avi because they think, well, whatever you find, you're going to say this is your asteroid. And it does worry me too, because one thing that's really interesting is that, I keep this, and we'll talk about this more on Thursday, but I keep saying that the oldest rocks that we've ever found, including meteors that we've dated on our own planet, do not reach past like around 4 billion years, right? And so my thought is, when I was talking to Avi, I was like, you have to date this thing if you find it, right? Because if you date it, and it's also no more than 4 billion years old, well, then you have a serious problem with your dating structure, basically, because there's no way that this thing came from another solar system that formed at the exact same time as our solar system. So the problem is that, well, if it dates to 4 billion years, maybe it's not the asteroid that he thought it was, because the bottom of the ocean is probably littered with asteroids is the problem, right? And so have you answered your question, or have you just not found the right rock? And the problem is, Avi is very cavalier with his ideas. I mean, he's championing this ET technology explanation for Oumuamua, and so a lot of the astrophysics community has kind of discounted him as a result of that. So as important as I think that finding could be, I think it's one of those things where it's difficult to prove a negative, right? Just because you find something, you can always make the argument, well, that's just one of our asteroids from our solar system. So anyways, it's really fascinating stuff. I recommend you guys. He's got tons of YouTube videos and everything. You can learn more about this guy. He's also...
You talk to him?
I've talked to him a few times. Yeah. We had him on the podcast twice. These 2 episodes, the last one was really good. I mean, he also just has a really... he'd probably make a hell of a physics teacher because he has a way of just using the most simple, basic algebraic concepts to relate things, right? Like when he talks about how to understand that the composition of something, it comes down to really the way that it breaks up in the atmosphere, and he can prove these things in very simple mathematical terms that anybody with a high school mathematics level can totally follow. And so I love that because I think that too often scientists get completely bogged down in the nuances of their ideas, that they lose sight of the big picture. And he's really, really fun to listen to and talk to because he has no fear of explaining even complex things to people who have no background in the subject matter. And so one of the worst experiences that I ever have on this podcast, by the way, is when somebody tells me that it's too complex and I can't understand it. When I hear that, I think you have no idea what you're talking about, basically. Because if you really understand something, you can explain it to your grandma. That's the truth. All right. So we looked at some of these maps. By the way, these asteroids do crash into the Earth pretty regularly. This is a map of bolide impacts. And we see some enormous scales of impacts. So the big scale, so 100 gigajoules. So 100 gigajoules, this kind of moderate-sized one, is about the size of the Hiroshima bomb, for instance, okay? And let's see, these are huge impacts. So very regularly, we have enormous explosions in the atmosphere. The good news is most of the Earth is not inhabited, right? Turns out we basically all live in tiny little places, which we call cities for the most part. Most of the world is completely uninhabited, so when they do crash into the Earth, it's not that big of a deal for the most part. But they're very, very common, even these enormous ones. Now, let's take a look a little bit closer. We're tracking these things like I mentioned to you guys last time, so it seems like we have a bead on about somewhere between 90 and 95% of the near-Earth asteroids that are bigger than a kilometer. So kilometer-sized impact is something that would absolutely disrupt everything on Earth. When I say disrupt, it would probably end civilization. It would be bad news. The 100-kilometer ones are going to end life, right? This is the dinosaur-ending impacts. So they're tracking these things, and they've got a good beat on most of them. But it does happen. This is actually, this is from a few years back. If this is going to play, I might have to go to the computer. This might be loud too, by the way. So hard to operate this behind me. Where's my cursor? About a decade ago.
Какой метеорит, блядь? Ебанулся. Нихуя себе.
All right, we could do this all day. One last one. All right. Yeah, so that one, by the way, is about on the order of the 100 gigajoules size, so the Hiroshima sized one. Now, nobody got killed by it. Sorry. Okay, but you get the point, right? And these are very, very common is the problem. This is just one that happened to be near a slightly populated situation, right? So they got some good cameras of it. But these seem to happen very regularly. Now, the reason this isn't that big of a deal is because it's blown up in the atmosphere, right? It's at the angle of attack is not straight down. It's kind of a glancing blow that this thing makes. And so those can be pretty serious. So this one, there was a really big one that appears to have happened in Russia back in the early 1900s. This was in 1908. It's called it happened at the Tunguska River, which is in Siberia, so no one was around. But it basically leveled something like 800 square miles of forest, right? Same sort of thing, that it blew up in the atmosphere and just destroyed everything below it, right? No trace of a meteor, by the way, ever found at this thing. Absolutely nothing. Completely vaporized in the atmosphere. But the shock wave from that impact was enormous. This is something like 10 megatons of TNT, so that's about as large as the biggest nuclear weapons that anybody has on Earth right now, essentially detonating in the atmosphere above this forest. Now, if this had happened over New York City or over Portland, that would be it, right? Now, so these things are pretty common, and that's actually quite scary. And they're blown up really high up, yeah. And so this is interesting because this is a sort of new topic for let's say, archaeoastronomy, people thinking about the things that have remodeled the surface of the Earth, because we've always thought about meteor impact craters, right? Well, we find the impact crater from the dinosaurs, right? The Chicxulub impact crater. But it turns out that most of the things that hit our Earth are not hitting it dead on like that. They're sort of skimming off the pond, right, so to speak. And that's really devastating too, it turns out. So, of course, like the point is that NASA's started tracking these things that are pretty large in recent times. I'm trying to let me see if I can get you the size of this crater. Or sorry, the size of this object. Let me go back one. Okay, so that one that I showed you, that we were looking at the pictures of from Chelyabinsk, it was about 20 meters in diameter, so pretty big rock, right? Now, NASA is only looking for ones that are over 100 meters, though. Now, if something in the sub-100 meter range was to detonate above a city, it would be pretty devastating. I don't think that it would destroy the city. This one, the Tunguska one, I'm not sure that anyone knows the size of it. I wish I'd written that down. I'll try to figure that out for you for Thursday, but it was bigger, to say the least. It was much bigger than that. So, really bad stuff, and we're just beginning to get a beat on these things. So, this is a sort of estimate of the different projects the different satellites that are tracking these bodies. You can see the field of them that are around us. This is our own Earth orbit, and some of the displaced asteroids that are potentially threatening us. You wouldn't need that big. I mean, like I said, when you're on the size of a kilometer asteroid, you're basically looking at something that would absolutely disrupt a country the size of the United States in a really bad way. But it might not wipe out the entire world. Once you get bigger than a kilometer, you're talking about the entire world being threatened, essentially. And so they're starting with the 1 kilometer sized objects and working backwards. But you know, if you see what a 20-meter object, the damage that can do, that thing was definitely blowing out windows and so forth, right? That's 20 meters, so that's 21 thousandths of a kilometer, right? And so they're only tracking things that are on the kilometer scale, right? So, yeah. And then, of course, I think they'll move back from that. So this SpaceGuard program is interesting. They're spending several hundreds of millions of dollars on this. And they're planning on tracking everything. Let's see. By 2028, they hope to have 90% of all near-Earth asteroids that are 140 meters and larger. So quite a bit less than a kilometer in the next decade or so. That's hopeful. So, you know, I spent a bit of time at the beginning of the course. We're going to run out of time. So I want to reassure everyone that there are a number of asteroid avoidance programs being constructed to date. All sorts of different ideas of how to do that. They basically can be binned into two categories. One is fragmentation, and the other one is something like reorientation. They call it DeLay, but it's basically just steering the thing away from us. Fragmentation is the less popular of the two because obviously if you blow something up, then you have more bits to trace and worry about. So that seems to be the less popular, although people are still entertaining that. It turns out that it's actually very easy to set up an orbiter around an asteroid and actually steer it out of the way, right? Just by putting a little moon, like a little satellite on it, you can change its orbital dynamics drastically. And you don't need to change it that much, especially if you detect it quite early. So we've done some different impactor studies. There was one on this asteroid called Temple 1, which was actually a comet they were playing with. They were able to change its orbit slightly just by crashing into the thing. And we talked about this. I believe we talked about the DART and deep impact missions at the beginning of the course. So I'm not going to go through those all over again for you. There are some impactor designs which are kind of interesting. You basically have this big long arm where you blow a hole in the surface of the thing with the first impact, and then the tower kind of collapses and the big charge is delivered at the end. So you basically make a hole for the bomb. You build a little bomb builds a hole for the big bomb explodes and pushes the thing off, of course. That's one idea. What else do we have? Different ways of directing, essentially light at it. So ion beams and really high intensity radiation. There's ideas of planting basically a rocket on the side of the things and just basically turning the thing into a spaceship. What else? This is a solar shield that somebody imagined could be developed to essentially steer the thing away with solar energy. It's an interesting idea. Railguns are an option. They call them mass drivers. So you essentially just slingshot something at it very, very fast. Railguns are really interesting. They make a big appearance in The Expanse if you guys ever do watch that. What else? Laser ablation. Everything you can think of, honestly. Attaching a tether like a ball and chain to the thing is another idea. I mean, basically anything you can think of, people are developing options for it. So I guess the good news here, one option is literally just painting the thing white so that it gets differential reflection and gets pushed out of the way by solar radiation. So everything that's possible, people are entertaining. And so it's a legitimate threat. It does legitimately happen quite often. Most of the Earth is not populated, despite what you guys probably think. It's mostly empty ocean and ice and uninhabited regions. And so it tends to not be a problem across human history, but it does seem to be a problem periodically. So let's see here. What do I want to finish with? Carl Sagan, who we've mentioned before, I didn't have time to get to comets, so I guess I'll say a few words about comets at the beginning of class next time. Carl Sagan wrote this book called The Pale Blue Dot, and they were just starting to churn up ideas about these things back then. And Sagan actually expressed that considering the history of genocidal political leaders in the past, that our ability to steer asteroids around would actually be a bigger threat by itself to us than the asteroids would ever pose by themselves. which I don't agree with him about, but I think it's a very legitimate point. Once somebody has the ability to move asteroids in their orbits and so forth, you have access to a potential existential weapon, an existential threat of a weapon, right? And so, you know, that's something to consider too, is like, can Earth as a whole make up laws and enforce them as a whole before we get out there? If we're all individual countries still squabbling over things by the time we're dragging asteroids around, it makes the consequences of our wars much, much, much greater. Anyways, I don't know what to say about all of that. The future is wild. I have no idea what's going to happen. I'm sure your generation will solve all these problems, so good luck. Anyways, guys, that's about it. So come Thursday, come early. I want to hang out with you one last time. And yeah, have a good rest of your week.